Welcome everyone. I'm Norman Wildberger. We're here at the University of New South Wales, and we're continuing on with doing some more computations of homology. So last time we started off with some very simple examples. We want to do a few more examples, maybe just a little bit more complicated. So a good place to start today is with the two-dimensional sphere. Let's compute its homology. Okay, so the first thing we want to do is we want to interpret or rethink about what this thing is in terms of a simplicial complex. So we want to construct it out of triangles, essentially. And there's a number of different ways of doing that, but probably the simplest one that would strike you immediately is to think of it in terms of it being a tetrahedron made out of four triangular faces. So let's do that. So here will be our tetrahedron. And the edge at the back there. And let's give it some labels. Call the vertices x, y, z, and w. And let's then write the space as a bunch of simplices. So in terms of simplices, x is going to be, well, we want to think about essentially the open tetrahedron. So we're not talking about a solid tetrahedron here, because that would be a ball. We're rather thinking about the four triangular faces with an empty interior. So that means that the simplices that we want to consider, in fact, are not starting with a 3-simplex, but rather 4 2-simplices, namely the triangular faces. So let's list them, and let's do it in a way that's kind of familiar from what we did perhaps previously. So we'll give this first face an orientation like that. Let's call it x, y, z. And then we'll say give this one here sort of an opposite orientation. No, that's the same orientation, going this way, so that it's going oppositely along that common edge. So that will be, say, x, z, w. And then how about the bottom? So y, z, w, and what direction do we want it to go in? Well, this one's going along this way on the edge, so we want the other one to go that way. So on the back, we'll go this way. And so that will be the orientation, say, y, w, z. And finally, at the back, the x, y, w side. How are we going to orient that? Well, the front face is going this way along this edge, so we want the other one to go this way, so it'll be going in this direction here. And that corresponds to, say, x, w, y. So we can think of it in terms of those 4 simplices. Those are the maximal simplices, the triangular faces. Of course, each one of those triangular faces has some subsimplices, namely the edges and the vertices themselves. But the space itself is determined by specifying the maximal simplices. So there they are. And now in terms of homology, well, we want to consider these chain groups, C0, C1, C2, C3, various boundary maps, and we want to then compute homology. So mind you, the boundary names are del 1, del 2, del 3, and this del 0 is really the 0 map. Okay, what do these chain groups look like? Well, the 0-dimensional chains are just combinations of various vertices. So that's actually, let me write it as Z4. Z plus Z plus Z plus Z. 1 for each of the 4 vertices. So a basis here would be X, Y, Z, and W. And the 1-dimensional chains are the edges. And let's give them orientations. So that the orientations, well, how shall we do that? Maybe say x, y, y, z, zx, like that. Actually, it's a little bit arbitrary. let's go this way. Doesn't matter how we orient things. So let's choose orientations. So there's 6 of them all together. So the C1 group will be 6 copies of Z. And the basis that we have is, let's list these things. So we have XY and YZ and ZX. And we said XW and WZ and WY. Two-dimensional cells, 2 simplices are the faces. There's 4 of them, so this is going to be another Z4. And this is spanned by the 4 faces, which are the ones that we're really starting with. So X, Y, Z, X, Z, W, Y, W, Z, and X, W, Y. And what about C3? Well, we said that we're not going to talk about the solid tetrahedron. This is an empty tetrahedron, a tetrahedron with a hole in it. So there are no 3-dimensional cells. So this is actually 0. So here's the complex of chain groups that we start off with to set up our homology. Okay, so what we're going to do now is we're going to compute cycles and boundaries at each stage, and then take quotients of cycles, mod, boundaries to get our homology. So the general formula is that the Hn, the nth homology group, is Zn mod Bn. And I remind you that Zn is the kernel of the delta n. Things that get set to 0, the cycles. And that the Bn is the image of the one higher boundary, n plus 1, del n plus 1. And those are called boundaries. And we want to take the quotient of the cycles, mod the boundaries to get the homology groups. Okay, so let's start with the 0 homology. So to calculate H0, well, first of all, Z0, the space of cycles, is everything, because this is the 0 map. Everything gets sent to 0. So that's just C0 itself. On the other hand, the boundaries, boundary 0, the boundaries here are the images of the edges under their boundary map. So we have to take all these edges, these 6 edges, and compute their boundaries. Okay. Well, so that's going to be the span of what? So what are the various boundaries? Remember, to take the boundary of an edge oriented xy, we just take the final minus initial. So the first edge has boundary y minus x, and then we get z minus y, and then x minus z, and then w minus x, and then z minus w, and then y minus w. So we started with C0 was just the span of x, y, z, and w. So we have this group mod out by these relations. And the effect of that, as we've seen last time, is basically to identify all the vertices. When we mod out by the boundaries, we're basically setting each one of the vertices equal to any other vertex. So this thing is just a copy of Z, and it's got a basis it's generated by, well, say just X plus B0. Everything is a multiple of just X, because any other combination, you can replace the Z with an X, and you can replace the Y with an X. You can replace anything with X, because these relations tell us that all 4 vertices are to be thought of as identical. Okay, and that coincides with our interpretation that we talked about last time, that the zeroth homology tells us whether the thing is connected or not. There's only one connected component, so the zeroth homology is a single Z to reflect that single connectedness of the space. Okay, that was easy. So now let's look at H1, the first homology. So H1 is 1 cycles over 1 boundaries. And so we have to compute the kernel of this map, and then we have to compute the boundary of this map, and then we have to take the quotient of those two things. All right, so let's see what happens here. Well, so Z1 is the kernel of del 1. Those 1 chains whose boundary is 0. Okay. So in other words, we're looking for combinations of the edges, and we want the boundary of that combination to be 0. Okay, so let's how are we going to find this thing out? So let's take a combination of the edges, say alpha xy plus beta yz plus gamma zx plus delta xy plus epsilon wz plus, say, eta wy. So that's a typical element in C1. It's a typical 1 chain. And what happens to that under the boundary? What happens to that under the boundary operator? Well, it gets sent to alpha y minus x plus beta z minus y plus gamma x minus z. I'm just using the fact that the boundary of any one of these edges is final minus initial. Plus delta times w minus x plus epsilon times z minus w plus eta times y minus w. And we're assuming that's 0. We're assuming that the boundary is 0. What does that tell us about the initial chain that we started with? Well, let's have a look at this equation, and let's sort of write it out in terms of the various elements x, y, and z. This is really the equation x times minus alpha plus gamma minus delta. And correct me if I do my arithmetic wrong here. That's the coefficient of x. And then what about the coefficient of y? So there's an alpha here, a minus beta here, a plus an eta here. Coefficient of z, a beta here, a minus gamma here, and an epsilon here. And finally, the coefficient of w, a delta, minus epsilon, minus eta. All of that's supposed to be 0. Okay, that means that each one of these coefficients is 0. So we have basically 4 equations in the 6 unknowns, alpha, beta, gamma, delta, epsilon, and eta. So we need to solve that system of equations. Okay, so we have 4 equations in 6 unknowns. All right, we do some linear algebra. So let's set up a matrix that represents this. And let's label the columns alpha, beta, gamma, delta, epsilon, and eta to be organized. I'm going to write down these equations in terms of a matrix. So we require that minus alpha plus gamma minus delta is 0. So minus alpha plus gamma minus delta is 0. Best of zeros. The second equation is alpha minus beta plus eta is 0. The next one, beta minus gamma plus epsilon equals 0. And finally, delta minus epsilon minus eta equals 0. Okay, it's fun. We can do a little bit of row reduction. But in some sense, we're doing row reduction over the integers here. It's a little bit different from linear algebra in that the coefficients that we want to use are only integers. We only want to do integer arithmetic because we're really working in a group. In other words, these coefficients are always integers. So we don't want to get any fractions. All right. So, okay, let's see if we can solve this. What are we supposed to do? We're supposed to row reduce to get it in row echelon form. So let's do that. So I'll rewrite it. Maybe I'll multiply the first equation by minus 1 to get it with a 1 here. And then I'll take the second equation maybe and subtract this new first equation, or maybe just add it to this one here. So if I add these, I get 0, minus 1, 1, minus 1, 0, 1. And this one I can leave where it is. And this one I can leave where it is. Okay, I hope you'll forgive me if I just work on here. So let me just multiply this second equation by minus 1. So I get a 1 here, so I can just use that to get rid of the 1 below it. So maybe I have room to go up here. 1, 0, minus 1, 1, 0. 0 is the first row. 0, 1, minus 1, 1, 0, minus 1 is the second row. Then I can take this row and subtract the first row. So this minus this is also 0, and this minus this is minus 1, 1, 1. And then this is the same up to a multiple as this last row. So at the next stage, I'm going to add this one to this one, so I'm going to get a row of zeros. Maybe I'll multiply this one by minus 1. And so I get one pivot entry here, one pivot entry here, and another pivot entry here. To get it in fully reduced row echelon form, I should get rid of the things above the pivot entries as well. So I'm going to add multiples of this row to the previous rows to get rid of those ones. So maybe I'll come down here. 1, 0, minus 1, 1, 0, 0. 0, 1, minus 1, 1, 0, minus 1. Oh, no, I'm going to add. So I'm going to add multiples of this one to the above one. So I'm going to take this row and subtract this one, which will give me a 0 there. Sorry. This minus this is a 0. This minus this is a 1. This minus this is a 1. And same thing here. When I take this row and subtract that one, I'm going to get a 0, a 1 here, and a 0 here. And then this row stays where it was, 0, 0, 0, 1, minus 1, minus 1, and a row of zeros. Okay, now we can read off solutions. There's a 3-parameter space of solutions. So let's call this parameter R, this parameter S, this parameter T, let's say. Our variables were alpha, beta, gamma, delta, epsilon, and eta. So in terms of these variables, I can now write that alpha equals I'll bring this to the other side. So R minus S minus T. R minus S minus T. Beta equals R minus S. Gamma is just one of the variables. It's R. Delta equals delta is equal to S plus T. epsilon was one of the variables, that was S. And eta was one of the variables, that was T. So I can write the solutions as alpha, beta, gamma, delta, epsilon, eta equals r times the vector 1, 1, 1 plus s times the vector minus 1, minus 1, 0, 1 plus t times the vector. Which one? Epsilon equals S. Thank you. Epsilon equals S, so that, and T times minus 1, 0, 0, T, 0, T. All right, so we've got these three basic solutions. So all solutions then, all solutions are multiples of the following cycles. This one here corresponds to the cycle alpha plus beta plus gamma. This one corresponds to minus alpha minus beta plus delta plus epsilon. And the last one, minus alpha plus delta plus eta. And geometrically, these are cycles which look like what? Alpha plus beta plus gamma, here I've labeled the edges. So alpha plus beta plus gamma, that was this cycle here. That does look like a cycle. And then minus alpha minus beta plus delta plus epsilon. So that's minus alpha, also minus beta, delta, and an epsilon. No, oh, here's the delta. Plus a delta and an epsilon. So that's the cycle that goes this plus this plus this plus this. That's also a cycle. It's a cycle with 4 edges. And finally, minus alpha plus delta plus eta is minus alpha plus delta plus eta. So that corresponds to that triangular face at the back. Okay, so there's nothing particularly unique, remember, about this basis. This is just a basis of the solution space, and there are lots of other bases that you can get by taking linear combinations of these. And if I took a suitable linear combination, I could probably, in fact, for sure, I could replace this cycle with 4 elements with a cycle of 3 elements representing one of the other triangular faces. It was just a question of the particular computation that I did and the particular row reduction that I did that I ended up getting these basis vectors instead of something else. Okay. So, the end result is that our cycle space is 3-dimensional. It's a group Z3 because it's got these 3 generators. Okay, what about the boundaries? Well, the boundaries. Let's go over here. So B1. So this is the image of delta 2. So when we're going from the 2 cycles, 2 chains, to the 1 chains under the boundary, what is the image of that map? In other words, what are all the possible boundaries of our 4 faces? Well, that's the span of the boundary of x, y, z. Here is x, y, z, that triangle. Its boundary is going to be alpha plus beta plus gamma. The boundary of x, z, w, x, z, w in that direction is going to be a minus gamma minus epsilon minus delta. So minus gamma plus delta plus epsilon. The boundary of YWZ, which is the bottom face here, YW face in that direction, is minus eta plus epsilon minus beta. So that's minus beta, I'll start with, plus epsilon minus eta. And x, y, w, that's the back face, its boundary is delta plus eta minus alpha. Delta plus eta minus alpha. Okay, we know each of these is a cycle. So now we have to compute Z1 mod B1. Okay, so Z1 was the group generated by these three cycles. And we know that this B1 is a subgroup of this. In other words, that each one of these can actually be written as a combination of these ones. The question is, what does the quotient look like? What's the quotient look like? Well, then you have to stare at things and sort of stare at these combinations and compare them with those combinations. But I guess we can see that this one here is already the same as this one. And I guess this one here, minus alpha plus delta plus eta, that's in fact actually exactly the same as this one. And what about the other two? Okay, so good comment. So we're saying that if we add this one and this one, then the alphas and betas cancel. That's good, and we get gamma plus delta plus epsilon, which is right here. Which tells us that the second one can also be written as a combination of these ones. So we've just concluded that this is actually the zero group, since the boundaries actually equal the cycles. So the quotient is just the identity group with a single element. So there's no homology, there's no first homology in the sphere, which is perfectly reasonable because the sphere doesn't have any one-dimensional holes. Okay, so finally now we are at the two-dimensional situation where we have to compute the two-dimensional homology. And let's see if we can do that here. So the two-dimensional homology is the two cycles mod the two boundaries. And so we now have to ask, well, what are these various faces, and what combination of faces will get sent to zero? And let me do that sort of geometrically instead of algebraically, although I could also do it algebraically. So we have these four faces. I haven't given them names: x, y, z, x, z, w, y, w, z, and x, w, y. And let's ask what combination of those things will have boundary zero. Okay, so we want to find, what's the what combination of these things here will have boundary zero. Okay, and I can argue geometrically this way, that when I take the boundary, say, of this face that's facing us here, I'm going to get this plus this plus this. If I want to get zero as a total sum, then say this face, this edge here that I've obtained has got to be canceled with something else. And the only thing that it can be canceled with is when I consider the boundary of the other face that meets at that edge. And the way I've set it up here is I've got the orientation of this edge going this way and this edge going this way in exactly the opposite way. And that means that the only way that the contribution of this edge to the sum being zero will be zero is if the coefficient of this face and this face are equal. They have to appear equally in order that there's cancellation and that the coefficient of this edge in the sum is zero. And the way I've set that up, that argument's going to apply to every edge. So the only combination that will give us a boundary is a multiple of the combination x, y, z plus x, z, w plus y, w, z plus x, w, y. So this thing here is indeed 0, as one can check either algebraically or just by the fact that I've oriented in such a way that the faces sort of are opposite along every edge. So this is the generator of the cycles. So Z2 is just generated by this particular combination. If I call these faces, say A, B, C, D for short, then I'm just talking about the combination A plus B plus C plus D. In other words, it's a single group, a single copy of Z. And what about the boundaries, the B2? Well, the boundary in B2 is all the things coming from C3. But we have no three-dimensional cells here. So there's no boundary at all. In other words, the boundary is 0. So the boundary is 0. And that means that our quotient, Z2 mod B2, is just a single Z. So H2 of the sphere is just Z. So in conclusion, we have found that H0 of the sphere is Z because it's connected. H1 of S2 equals 0. There were no one-dimensional holes. And H2 of the sphere is Z. What about the higher homologies? They're all 0 because, well, all those chains are all 0. So Hn of S2 equals 0 for n bigger than or equal to 3. So that was a reasonably involved computation, although we could have made it simpler by taking some shortcuts and so on. But just sort of to illustrate that in some sense it's all rather cut and dried. A computer could do this. Right? We could start off with a list of simplices and we could program a computer to set up these linear equations and to solve them and to compute homology. Well, we would like to compute some more homology, so it's worthwhile thinking about whether we can do this in a simpler way. And it turns out that there is a much simpler way of thinking about the kinds of ways we're representing spaces as simplicial complexes that makes computation like this one much simpler. Okay? So this is maybe the official definition, and now I'm going to give you a variant which I think has only come into focus in the last 50 years or so, maybe starting with the work of Wildberger in the 40s, who introduced something called semi-simplicial complexes, which maybe now, following Alan Hatcher's book, we'll call them delta complexes. So with a delta complex, we become a little bit more flexible, less stringent about what actually a combination of simplices is going to look like. We are allowing ourselves to think not necessarily of a geometrical object in space made of honest simplices, but we're prepared to have our simplices be curved. And in fact, we are also going to allow them to meet themselves on the boundaries. Okay. So let me illustrate that by giving you another version of the sphere. So another computation of Hn of the sphere by thinking of the sphere in a different way as a simplicial complex. By thinking of the sphere as the following. We've got one triangle here, let's call it A, and let's give it edges x vertices x, y, and z, and we'll orient them like this, let's say. And then we have another simplex B, whose vertices are also x, y, and z. And maybe we'll orient it in exactly the same way. And what we're going to do is, we're thinking of these edges, so let's call that A, B, and C. Those edges are supposed to be exactly the same edges as those edges. Now, in three-dimensional space, you can't glue two simplices together along the boundaries without gluing the simplices together. But if you allow them to be sort of curved, then we have a situation where we have something like this. We have there's a base triangle, and it has a kind of one simplex on top of it, like a cover on top, and then it has another cover on the bottom. Maybe not a very good picture. So just think of sort of a cap, a spherical cap. So the simplex is not flat, it's capped a little bit like this, and there's one on top, and there's one on the bottom, and they just mesh together. All right, now our computation would be a lot simpler if we only had this story here, because then our C0 would be just the span of x, y, z. Our C1 would be the span of A, B, C. The span C2 would be the span of A and B. Everything else would be 0. So let me just show you the computation for the H1 in this story to compare it to the computation, the rather laborious one that I did with all those linear equations. So let's compute H1 in this story. So what are the cycles? So we're looking at combinations of A, B, and C. So maybe alpha A plus beta B plus gamma C, and under the boundary map, that is sent to A gets sent to y minus x, B gets sent to z minus y, and gamma gets sent to C gets sent to, this one here should be this way. Sorry, they're all going in this direction. C gets sent to x minus z. And we want to set that equal to 0. And so then the equations are x minus alpha plus gamma plus y alpha minus beta plus z beta minus gamma equals 0. And that happens precisely when alpha equals beta equals gamma. And so the cycles are just the span of A plus B plus C, which makes sense. That's our basic cycle in the story. What about the boundaries? So B1, this is the image of delta 2. Well, what is delta 2? Here's delta 2 here. What is the boundary of A? Well, the boundary of A is, well, let's orient it like this, and let's orient B in the same direction, so it's all pretty easy. So the boundary of A is A plus B plus C. The boundary of B is also A plus B plus C. And so the image of the boundary is just multiples of A plus B plus C. And so obviously now Z1 equals B1. So that means that our first homology is 0. And what about our second homology? So that's Z2 over B2. Well, that's going to be what? So what is the kernel of del 2? Which combinations of A and B are going to get sent to 0? Well, I think it's pretty clear that if A gets sent to this and B gets sent to this, the things that get sent to 0 are the differences capital A minus capital B. So this is just the span of A minus B. And the boundaries, that's the image of delta 3. Well, again, that's before that's 0. So the Z2 is isomorphic to a single copy of Z. B2 is 0, so H2 is a Z. So this is a dramatically simpler way of thinking about computing homology when we allow ourselves more flexibility in interpreting what we mean by a simplicial complex. And now in the next lecture I'm going to show you how to extend this to the torus and to the projective plane. So when you have a torus, well, triangulating a real torus involves quite a lot of triangles if you're going to do it honestly. Okay? If you want to triangulate a torus in a kind of a way where every piece has distinct boundaries and there's no overlap, you have to do something like this. Use something quite a large number of triangles. But with this delta complex story, we're going to almost cheat. We're just going to triangulate the torus in the most simplest possible way like that and compute homology from that. So that's what we're going to do next time. I'll see you then.